the afternoon for some organic chemistry. A little bit of tea. I'll get around to that later. Organic chemistry revision. People ask for a revision. I asked people what they wanted. Some people said organic. So here we go. Organic stuff. I'm going to do organic mechanisms. I just want to say a little bit about organic chemistry first of all. To me, organic chemistry, there are three things you need to be able to do successfully. First one is the type of chemical you've got and therefore the name that it has. If you can do that, that's one of the three skill sets. So that's the first one, type, which includes naming. Then there's the sometimes quite overwhelming reactions and the reagents that you need to know to convert organic chemicals from one type to another, change the functional group. Around about 60 reactions you need to know what to do, how to do it, what you use in an A-level chemistry course. And then there's mechanisms. Mechanisms is a smaller set of reactions. You need to be able to apportion a mechanism to a limited set of reactions at A-level. And this video is going to focus on mechanisms. Before we can go wading into mechanisms, there's a couple of things we have to make sure. Firstly, do we know what a mechanism is? Mechanism is when you look at a reaction, it doesn't just go, oh, done. It's what stages does it go through, or what sort of sub-steps does it have. It's like when you make a cake. You don't go, here's the ingredients, oh, there's a cake. You go, here's the ingredients, first thing we have to do is this, then we have to do this, then we do this, and we put it in the oven or whatever. And then we ice it if it's Christmas. That's like a mechanism. So you break it down into stages that take place. And when you get further into chemistry, one of those stages will control how fast the reaction goes. That's called a rate determining step. That's a year 13 discussion concept. Now, when it comes to mechanisms, which is what this is about, there's a couple of things that we need to establish. First of all, the types of reagents, I suppose, the types of chemicals that you're going to use. Free radicals. One of the classic mechanistic questions is to do with free radicals, so we'll have a section on that. As you will see, I'll explain about how we're going to do with these videos. So free radicals. First thing, what are they? They have an unpaired electron. Most of the time electrons on chemicals are an even number, and therefore there's not an unpaired one. They're all paired up. When you get an unpaired electron, it's termed a radical or a free radical. In terms of your real world thing, free radicals inside your body are very bad for you. They are linked to cancer, I believe. How are they formed? Well, I'm sure there were lots of ways of forming them, but at A level, the only way you think about forming them is ultraviolet light acting on something that is diatomic. That diatomic is a halogen. So, and it's because the size of the UV photon is the same size as the bond energy of a interhalogen bond. So ultraviolet splits that up. So what you get bromine, for instance, would have a dot and cross diagonal like that. What you do is you send one electron that way, one electron that way, and the result, it's not negative, it's not positive, it has no charge, it's a bromine atom, and of course there were two of them because you started with the Br2. So free radicals. Then the other two electrophile. Electrophiles will have some way of being positive or partially positive. So what you're looking at is either something that is positively charged. Now most of the time that's a metal ion and they don't do organic chemistry, at least the majority of the time. So what you're looking at for almost all organic reactions, although there are some exceptions, is something that carries a partial positive charge. So when you look at something like that, that's the electrophilic end of that molecule because it's delta positive. There are times when you see, and this is a year 13 thing, you get that, which is also an electrophile, NO2 with carrying a plus charge. Well, that'll be an electrophile as well, but that's used in benzene chemistry, which is not a year 12 thing, which is what I'm doing at the moment. And then you have nucleophile. Now nucleophile, a bit easier to think about really, because it's the opposite. It's going to be a negative, either fully negative or partially negative. So you will get such things as things that are completely negative will be a nucleophile, Br minus, OH minus, all carrying a whole negative charge. Yeah. You will have things that are also not carrying a negative charge, but ammonia got an electronegative atom and lone pair. That makes that delta negative, and therefore that is going to be the nucleophile. Water will also fit that criteria because the oxygen is delta negative in water, two lone pairs as well. So therefore you will get water behaving as a nucleophile. So you can get nucleophiles that are either carrying a partial negative or a full negative. You can get electrophiles partially or fully charged. And that kind of finishes the introduction with the types of things. So there are just three types of reagent. There are the free radicals, really only occurs in one situation. Electrophiles, there are a whole load of reactions involving electrophiles, and then similarly a whole load of reaction with nucleophiles. And that's it really. So what's going to happen now is that there are going to be three versions of this. One of them is going to go on to do free radical mechanisms, one of them is going to be about electrophilic mechanisms, and the other one is about nucleophilic mechanisms. And it'll be whichever one follows what I'm saying now. I'll see you after the edit. Bye bye. If you're here for the electrophilic mechanisms, we're talking year 12 electrophilic here, so we're not talking the electrophilic reactions that go with benzene rings. Now I'm sure that'll be in another video one day, but right now this is focused on the year 12 content. So this is going to be electrophilic mechanisms, and this means alkene chemistry. So we're looking at specifically, because it is the only example, addition reactions with alkenes. So electrophiles, there are the polar ones, something like HX, where X could be a Cl, Br or I. Now that means it carries a permanent dipole, delta plus and delta minus. You also find that in sulfuric acid, which also the hydrogen is delta positive because it's attached to an oxygen, which is delta negative, and the non-polar, something like Br2, which is an example. But I know that's not right. We don't want to know. We want an X2. So that's an example of X2. People use bromine a lot because it's kind of intermediate. When you look at this here, hydrogen halides, when you do addition reactions, hydrogen iodide reacts really easily, but it's really hard to make. Hydrogen bromide much more simple to make, although you can't actually have hydrogen bromide, you have to make it when you want it. Hydrogen chloride you can have all the time, but it's not very good at reacting, and hydrogen fluoride is unutterably hopeless, because once it's got the hydrogen it doesn't want to let go. So you kind of pick bromine most of the time if given a choice, because it's sort of intermediate. So you have to, and these are the ones that we have to consider at A level: hydrogen halides, sulfuric acid, that's conc sulfuric, not dilute, and bromine as an example of a halogen. When you talk about the organic, meaning the alkene, you have to consider the consequences of symmetrical and non-symmetrical alkenes. So we'll start with symmetrical. Now symmetrical merely means that the molecule is the same number of carbons on both sides of the double bond. Well, if I pick one double bond, it's symmetrical. So if I pick that, if that was a CH3 and that was a CH3, and it would be a butene. Of course there are two types of butene, E and Z. In terms of the mechanism, it's the same at A level. And we then have got, how do we get a mechanism for the, well, the mechanism for the polar ones and the non-polar actually have a fair degree of commonality. So the easiest one to get your head around, to get you in the sort of right sort of things to do, is something like HX, where you fall into the standard trap, HBr, because it's sort of intermediate. So when you look at an alkene, a double bond, 2 sigma electrons, 2 pi electrons, that makes 4 electrons. So the double bond is quite electron rich. Now that means that there must be a delta positive somewhere outside, or be at both ends. But the delta negative is in the middle. If it's completely symmetrical, it's non-polar, but it's still got 4 electrons. It's electron rich where the double bond is. And that means that the HBr will find it terribly attractive to go, I'm delta positive on the hydrogen, and be pulled inexorably in a sort of attractive fashion, much like a love affair, towards the electrons in the double bond. Now, then we now reach the point of we need to do the correct arrow. What you do is a double-headed arrow. So a double-headed, and they're always curly arrows, they're not straight arrows. Straight arrows are reaction arrows in equations. That represents 2 electrons. The free radical one, if you were doing it, where you use a single electron, that looks like a 2, there we go. Free radical electron, where this half-headed arrow would represent a single electron. But of course that's not relevant to what we're doing, but that would have been relevant if you were looking at free radical formation. And so, double-headed arrow. Now one of the mistakes that people do is they trigger the mechanism the wrong way. They go, I'm reacting with HBr, that'll be the trigger for what I do. That is incorrect. The electrons, there are, well, 4 of them in the, it's the pi electrons that are going to be the ones that come out. They come out and they grab the hydrogen, and the hydrogen offloads its electrons towards the electronegative bromine, because the delta negative will take the electrons down towards it. Now, as a result, we get, and because mechanisms are about steps, so this then, as step 1, then becomes, what do we get as a result of step 1? Well, if we picked the hydrogen onto the right hand carbon, of course it makes no difference, it could have been picked onto the left hand carbon. What happens, and correct shape drawing required here as well, is that we pick the hydrogen, it goes on as a plus. Now some people go, oh, why does it go on as a plus? It's quite difficult to get your head around. Well, hydrogen contributed 1 of the electrons in the HBr bond, and both of those electrons went on to the bromine, so the hydrogen lost its electron. Therefore it came onto the molecule as an H plus here, but this is the place where the carbon has not got the right number of electrons, it's short of electrons, so it's going to be plus. And you have formed in that, well, here's the word. You formed a heterolytic split. It'll be Br carrying a full minus charge. What will then happen is the attractiveness of, oh look, negative to positive, inexorably drawn in a love affair way towards the positive, with the word heterolytic, and the result of that is that you now, in full-on displayed form, form bromoethane. So the reaction is ethene plus HBr forms bromoethane. Only product, because addition reactions only have one product. So that's an example of a symmetrical. In a symmetrical, it doesn't matter which side you put the plus, because the product will come out the same in both cases. Now we're going to take a little pause whilst I just clean the board off so that we can do the non-symmetrical version shortly, but I actually need to do the mechanism for sulfuric acid, and I also need to do the mechanism for bromine. So we need a little bit more space to get some more things on the board. So I'm just going to take a little pause and I'm going to clean the board up, and I'll see you on the other side of the pause. Oh, it caught me having a little tea break in the middle. So I've prepared the board with a little bit more about the sulfuric acid. So sulfuric acid, H2SO4, structure of it is that, delta minus on the oxygen, delta plus on the hydrogen. The mechanism's going to work the same. The electrons here are going to go grab that, and they're going to go to there. So that makes these. Now I didn't mention the generic name for these. Carbocations, positive carbon ions, sometimes called carbonium ions as well. So that carbocation, same one as last time, that's part of the commonality between the two. And then what has been formed? Has been formed that hydrogen sulfate ion. Oh, that's a terrible H. Right. And what will happen? It'll work its way through the word carbocation because I've written it in the way, and it will go in and join on there. So the product would then be in full displayed glory. Alkyl hydrogen sulfonate. So there would be the product, mechanistically no different to the HBr. It's just that all of this is taking the role of the Br that becomes Br minus and then goes on. Now if you were to do this and you required a non-polar, bromine is going to be our example, mechanistically it's not massively different. It's just the starting step requires a little bit of a, quite frankly, a bit of a leap of faith in my mind, but it's the way that it goes. So you can see my board doesn't go clean, it's getting a bit overused over these weeks. So what you have is now, with our non-polar example of bromine, bromine comes and we need to induce a dipole. Nearly spelled that wrong. Induced So by virtue of approaching the 4 electrons in the double bond, and there is a sort of arrival in the right orientation thing here required. What will happen is that it will push electrons away from the double bond, because electrons are negative, electrons repel electrons, so it will push them down towards the other bromine, forming a delta positive, and then the mechanism is the same. Only this time the product is going to have 2 bromines in it. So this time what you have done is you have joined a bromine instead of the hydrogen from last time. But you've still got a carbocation, and then you've got Br minus. It will be inexorably love drawn towards the plus, and the product in full glorious displayed is a dibromo, in this case 1,2, but on the 2 carbon atoms where the double bond was. So the bromine will identify the position by virtue of where the 2 bromines go on where the double bond was. If there were 2 double bonds, it would take 2 bromines and react both. Of course you'd need to add twice as much bromine as you would if there was a single double bond. Now that is the symmetrical mechanism, where it doesn't matter which side you start, which side you put the plus, and whatever. When there's non-symmetry, or when it's asymmetrical, which is the proper word, we get into the territory of having to consider which carbocation is the more stable out of the 2. It's not that difficult, but I'm going to take a little pause whilst I spray the board to get it not so blue, and I'll see you on the other side of my cleaning. See you soon. So, non-symmetrical propene, simplest example, I have to be honest, simplest example. Now we've got 3 things that we talk about doing addition reactions with. Bromine, the fact that it's asymmetrical makes no difference at all to bromine. You'll put 1 bromine on that carbon, 1 bromine on that one, and it will be the same mechanism as before in terms of what you do, because nothing you can write would be wrong. I'll be honest, there is a correct and an incorrect version of the carbonium, but you'll see that when we do HBr. Sulfuric acid, which I've written in a weird way, but sulfuric acid will do the same mechanism as HBr, because it's H and then the negative bit, SO3H. So I'm going to get rid of those just for a moment, and we're going to go through what happens. Now, the reason it becomes a little more thought involved is that when you come out and you grab the hydrogen and you do that, and it's called arrow pushing, which I didn't mention before, but people call it arrow pushing. That arrow then pushes that arrow. When it's written like that, that says that that hydrogen is going to go to the carbon where the curve is. So it could have come out that way and picked the hydrogen onto the other carbon. Now, one of those 2 choices of picking up the hydrogen there or picking up the hydrogen there, one of those is energetically more stable than the other, and therefore the consequence is that firstly you get 2 products, secondly you don't get equal amounts of the 2 products, and therefore you have to understand why the carbonium or carbocations exist for, well, basically different amounts of time because of the stability. So if you were to, if you were to go, you would, and put it in 2 choices, you can have that, and you can have has the two carbocations. Now this one, because it's got two hydrogens on it, is termed a primary. Remember? Primary because it's got two hydrogens. This one is a secondary. So this is, now you often see primary written and secondary like that. Can't do that in an exam paper. I can just do that on the board as a memory thing. But you have to write it out fully. So primary and secondary. Now, the more carbons that are attached around where the plus is, the more stable and therefore energetically stable and therefore the longer lasting the carbonium ion will be. Primary has only one carbon attached there. One for the one primary. That makes it less stable. This carbon here has got this one and this one, so it's got methyl on both sides, it's more stable. And therefore, this lasts longer than that. This does more reactions than this one. This results in a product that occurs in a larger amount than the product formed by this. You still get a reasonable amount of this one, but you get way more of this one. So what happens, of course, is the bromine goes on there, and the bromine goes on there, and you get two products. So that one, where I've put the bromine on there, produces 2-bromopropane. This one here, kind of done a different formula there, but it puts the bromine on the end and produces 1-bromopropane. Oh, I'm in trouble saying that. Major and minor. Major meaning more. So that there, that there. If you use sulfuric acid, same. Major, minor. Don't have to know the percentages, but if you think of it roughly as 60-40 or 70-30, you're in the right area for how they do it in terms of percentages. So there you have asymmetrical. Now if you were to take it to slightly more complex molecules.
It's not cleaning the board. We're going to have to take a pause whilst they spray the board. Be back in a moment.
So something a little more complicated. Here we have alkene with a number of carbons around the double bond. It's 2-methyl but 2-ene. Carbonium or carbocation wise, two choices, either end of where the double bond was. Which one is more stable? Well, neither of them are primary for a start, so this would mean that the percentage difference between major and minor get closer together. This one, 3 carbons attached. Tertiary. Tertiary is better than secondary, is better than primary, so that'll be the major, or the major carbocation, and therefore leads you on to the major product. Here, carbon, hydrogen, carbon, secondary. That'll be the minor product, but like I said, the percentages will be a bit more similar than they would be when there was a primary involved in the decision. So that's a quick go through. There is also attached to this a set of questions for you to practice your mechanisms on. And then, well, I'm not going to do the answers as a typed up set of answers because they take ages to draw out mechanisms. So what I'm going to do is I'm going to have a separate video, which I haven't filmed yet, where I go through the answers to the mechanisms. And, well, that's a quick run through of electrophilic in the context of Year 12. That means electrophilic addition reactions of alkenes. As I said earlier, year 13 does have electrophilic substitution reactions of benzene rings, but that's not what this is about. This is about year 12 revision. There we are. There's a third video, Nucleophilic. If you want to see that one, that'll be the third one of these. But thank you for watching. Good luck with the questions, and you'll see the answers when they've been filmed. I'll see you soon. Bye bye.